Great. So I'm going just type solutions. So for the first one, what we got was 2x plus 5. If you disagree, type it because I could make mistakes. Okay, for the second one, what we got was minus 3x to the power of minus 2. Great. Then for the third one, oh yeah, I should do it like that. So, 1, 2, nice, 3, x plus 5, yeah. Okay, started on a good note. Why is it 2x? Why is it just x? Is because we were supposed to multiply 0.5 by 2, so the coefficient by the power, the exponent, and we obviously got 1. Yes. Yes. Yes, you're right. Great. Thank you. Let's move on. So here we have a fraction of 1 over x. That's just standard log, plus 4. Got that correct. Then we have 2e to the power of x. Right? E to the power of x doesn't change. Plus 3e x to the power of e minus 1. Okay, great. So far so good? Cool. So x, this square root that is actually cubic root, it's the same as x to the power of 1 over 3. So what we're getting is, if we write it nice, 1 over 3, and then x, which power is getting here? You can type it real quick. Yes, so correct. Both answers are correct actually. Why? Because if we write it straight in the denominator, as I prepared to do it, the exponent will be positive. If we just write it in a line, it will be minus 2 over 3. So, like that. 2 over 3 here. Or what you could get also is a fraction for 1 over 3, because that's for sure. And then x to the power of, and here what you could write was 2/3. So both of them are correct, and nobody is going to tell you anything for not putting the positive exponent and putting it in the denominator. I just like positive exponents. Well, here we could also write it in a fraction. What about the second? Yeah, exactly. So I could write here this way. So that would be minus, and that's fraction 3 over x squared. Okay, yeah. The second term in 5. Okay, sorry. We had 5x to the power of minus e over p. Very ugly. So this is the derivative of the first part. Let me keep it this way, right? And then were supposed to write plus. Okay, step by step here. 5 times minus e over p. Both e and p are numbers, right? Pi. Sorry. Sometimes my Russian is just stronger than me. And then we have the exponent here of fraction e over pi minus 1. Okay, so let's see. Everything good? Supposed to be. So this is the coefficient. No, don't tell me. Okay, cool. This is the coefficient that was just of x. Then x had this power, and even if it's ugly, it's okay. Well, we could try to simplify it, but okay, great. 6, we have just one term, which is great. E over x to the power of e. So e stays as a coefficient, and then this means that x was raised to the power of minus e, since it is in the denominator. So we have ex to the power of minus e minus 1. Okay, great. Now 7. Here we have 2, so we have 4 e to the power of x that we've seen. E squared. Where do we have e squared? Where is e squared? Why am I supposed to have e squared? Okay, this is a better question. Yes, it is negative. Yeah, for number 6. Though, why is squared? E, what, yeah. Okay, now I'm going to explain myself and you too why it's e squared. So, as I was saying, e is a coefficient. Yeah, e here is a coefficient, and then we have e raised to the power of minus e. So we leave our coefficient, then we have to multiply it by the power, by the exponent, and then x gets power of minus e minus 1. So yeah, this is good. For minus 2 e no, it's not, yeah, it's not minus 2 because we have e times e. Good. Now here, okay, I know. So that will be 2 is a coefficient, minus 2 is a power. So eventually we get minus 4. And then the power of x will be minus 3. That's right, right? So the same logic as for e. So here we have negative. We have to have negative because the power was negative. And the exponent for x is just smaller by 1. Okay. 3 logarithm x plus... okay, well, let's rewrite it first. Because like this, it's really weird to write it. So negative exponent of x means that we were supposed to put it in the denominator. So we're ending up with a 3 floors fraction, and this is turning to just x to the power of 1 over 4. Oh, wait a second. So this is also good, right? All good? Give me plus. Thank you. Perfect. So now the product rule. Again, we are going to use it even though the first one is easier without it. So the derivative of the first term of a product is 1. So we just have for the first this. And then we have plus. And we are taking the derivative of the second. Oh, 8 solution, yeah, exactly. I rewrote it very happily, and what am I doing then? X to the power, we had a fraction. 1/4. Okay, so the derivative of this, now, this is what we're supposed to do. X. The derivative is equal to, here we're getting a fraction of 3/x. And then plus 1/4 x to the power of, well, let's write it here, the x with a positive power, 3/4. That's good? Everybody agrees? More pluses. Thank you. Okay. Great. So let's move on. The product rule that I started. So that's for the first term, and for the second term we're going to have the derivative of the second part times just the first part, which is x. So it's going to be 8x squared. Okay, is that clear? Because we were supposed to just multiply by x and then we get another x, and here, well, it is really not nice to leave it like that. I'm telling you not to simplify anything, but it was just too not nice to not simplify it. Okay, cool, perfect. Then thank you, I appreciate pluses. Then the number 10. Number 10. Okay, here it makes perfect sense to use product rule. So e to the power of x times logarithm x plus, we can write it in a fraction like that, e to the power of x over x. 1/x is the derivative of the logarithm, and the first part we leave it. 11. So again, thank you. Again, makes sense to use product rule. So the derivative of the first part, that will be, we have to here multiply 2 by 1/2 as an exponent of x, so we get just 1 for the coefficient for the result, but x is raised to the power of minus 1/2. Minus, how do I do minus? Minus 1/2. Okay, perfect, plus 1. So that's the first part, and then we have to multiply it, let's put times, by the second part as it is, so 3x plus x cubed, plus, then we take the derivative of the second part, that becomes 3 plus 3x squared, and then times the first part, and the first part is 2 square root of x plus x. Okay, perfect. So I think this is also correct. That was nothing to make a mistake here. Well, I can make mistakes anyway. Okay, great. It's good. Then our number 12, which also makes sense to do product rule. Just I want to rewrite it again. So for you to get used to nicer notation. So here we have a lot of stuff, and you could make again a mistake. We have minus, we have ln x plus 3x, we have times, and that's what I want to rewrite. 3 times x to the power of 3 over 4. So this is again for those of you who don't remember very well how to deal with exponents. This can be rewritten like that, and it's easier right now to take a derivative because we see exactly the power. And also here, to make it very, very, very easy, I want to just deal with actual variables. So I put 3x, so this 3 I can put it in the beginning, and then I'll have to just write it once, and the rest derive according to a product rule. So 3 over 4. Great, we have this. So minus 3, we can just leave it like that. Well, okay, this example I gave you exactly with this purpose, so you know how to deal with the coefficients. So let's stick this minus 3 to the first part. So we can say that the first part has this as a coefficient, and I think, well, it's better maybe to, no, but whichever part you can stick it to. So let's say, so this is the first part together with minus 3, and this is the second part. Okay, cool. So now the derivative of the first part will be minus 3 because we don't know where to put it. And here we're getting our fraction of 1 over x plus 3. Okay, cool. So that was the derivative of the first part, and the second part we leave it just here. Then we have to do plus the derivative of the second part times first part. So actually the first part is negative 3 with the coefficients, so I can write it already here, so I have it and I don't forget it, because that's what I usually do. And here we were also supposed to multiply it by 3 over 4, which is the exponent of x, so here fraction 3 over 4. And x is getting its negative power now, and it's a fraction 1 over 4 negative. Okay, negative 1 over 4. Perfect. That was number 12. Took me some time. Number 13. Okay, again we have this minus 2 that we can stick to the first part. So let's say, again, let's rewrite it so it's easier to see. Minus 2x to the power of a fraction 1 over 3. That's what this cubic root means. Times e to the power of x. E to the power of x is the best thing that can happen to us. Okay. Great, so the derivative of the first part will be minus 2 over 3 because we have to multiply by 1/3 x, let's put it here, I like it better, x power fraction 2 over 3 times e to the power of x, and then we have plus the derivative of e to the power of x. E to the power of x, let's put minus because we are multiplying it by this, and something like that will be the answer. Again, doesn't matter the order. Okay, perfect. So that was the 13 numbers done. Now let's move to the fractions. And here, nothing super crazy bad, but well, these examples I think are better than those that I gave you in class yesterday. So just pay attention and make sure I'm making no stupid mistakes. Okay, so now I'm working with the first one. Okay, so here you see the beautiful 1 over 3 and the power of 3. So we end up with just x to the power of 2. That's the derivative of the numerator. Then we multiply it by the denominator, which is 2x plus 1. Then we do minus because now we changed a different rule. The derivative of the denominator is 2 times the numerator, which is 1 over 3x cubed. Cool. That was number 14. For number 15, what we got? Another fraction again. So the first thing first, the numerator, which is quite long here, squared plus 2x squared. Then the derivative of the numerator is very sweet again. So that will be just that times the denominator. Good thing I already typed it here. Minus the derivative of the denominator. Well, that's something. So first of all, we're going to have a fraction of 1 over x. Then we're going to have x to the power of e. Then 2. Okay, I hope so. And we multiply it by... Oh no. Again. Why not exactly? Yeah, that's a correct question because I'm taking the derivative and it's not e to the power of x, it's x to the power of e. So I was supposed to do what I've always done with this thing, like that. Yeah. Cool. I'm lucky that I have you all. Perfect. And then I multiply it by the same thing. Well, I can put it here. Makes sense. Okay, that's the answer. Great. Then it will be better. Okay, number 16. Fraction. Then x power 4, because we had x squared, we put it again squared, blah blah. The derivative of the numerator will be 1 over x, but then we're gonna multiply it by x squared, so we actually end up with with just x for the first term. Then we do minus. Here we have to get the derivative of the denominator, which is just 2x, and we multiply it by ln x. Good? Good. Perfect. Number 17. Okay, number 17 is also not that bad. Ending up with a fraction, and here we're gonna have a square root cubed of x squared. Again, a nice example of how exponents work. So then here the derivative of the numerator will be our favorite. Plus 1 over 3, which is the power, the exponent. 1 over 3, we've seen it already many times today. Now x will be to the power of here, I'm going to leave it in the denominator. The power will be 2 over 3, fraction, 2 over 3. That's the derivative of the numerator, so we can put it nice like that. We know that we have to multiply it by the denominator. So let's put it in front here, and it's not squared because it's just numerator, denominator as it is. Perfect. It's weird, but I think it's okay. And then we continue in the numerator, and no. Why is the denominator not x cubed? Because it was... We're doing 17, right? Okay, we're doing 17. Yeah. It is. It was not a cubic square root. I'm sorry. It was just normal square root. And then we square normal square root and we get x cubed. I should have more people checking my stupid mistakes. Come on. I could tell you that I'm doing it on purpose to test your attention, but no. Okay, so is this fine? Okay. Great. Now the derivative of the denominator. So the exponent was 3 over 2. Now that's what we're gonna write. 3 over 2 x to the power of, okay, which power? Type it, please. Okay, I agree with 1 over 2. I don't agree with minus 1 over 2 because the power was, the exponent was 3 over 2, right? And we do 3 over 2 minus 1 and we get just 1 over 2. Cool. 1 over 2. Or I could just write it as a normal square root, but doesn't matter again, whichever way you prefer. And then I multiply it by the denominator, which is... well, here you were supposed to get this nice thing, so let's simplify it a little bit. Now I'm multiplying it by x to the power of 3 over 2, which means I'm just adding this power. So also too nice not to simplify. And we're gonna end up here with which power? Like, what exponent will x get now? Mm-hmm. 4. Yeah. And that's beautiful. So for once we can simplify. You could just write times the square root of x cubed. Great. Now number 18. Well, you have to make sure that it works. Oh, why not? Yes. The very left in 17 on the top. Yeah. Because for some reason what I was seeing was the other way around. X squared. Cube. So, you know, I'm always telling you this is the worst. Here you make a lot of stupid mistakes, and now you probably wonder how I passed PSME. But that was a real issue, for example, for my micro exam, because I saw something. I mean, I read the the exercise, and in my head I created different numbers. So that's how I passed my first midterm, like I got 13.4, something like that. But well, eventually everything was fine. But this is not my strong side. Oh, there's an error. Come on. Which one? Where? Yes, please unmute. Mm-hmm.
Should it be minus 3 by 2 to the power x to the power half into e to the power x plus x to the power 1 by 3?
Wait. Yeah, I see. No, I see. It has to be times the numerator, right? Yeah.
X to the power half.
Wait, I'm gonna redo it. So it is the derivative of the denominator times numerator. So the derivative of the denominator, we got it right. It was a fraction of 3 over 2. And then x to the power of 1 half. Okay, what did I do? I multiplied it again by the denominator. Okay, why not? Okay, then here what we're supposed to write is just the numerator as it was. So ex plus, what was that? Okay. I know, that's why. That was the problem of the whole thing. Okay, pluses, minuses, angry faces. Okay, cool, thank you. Number 18. Okay, I'm gonna get it right. Denominator squared. So logarithm x plus e to the power of x squared. Then numerator. The derivative will be negative 2 over 3 x power negative because it is minus 1 over 3 minus 1, and we're ending up with a fraction 4 over 3. Then, this is the derivative of the numerator. We just multiply it by denominator as it is. Then, the derivative of the denominator, we can already write the numerator because we're just multiplying by it. And that's a good habit that I actually don't have. So just write the function as it was and then deal with the derivative. And the derivative here will be 1 over x plus e to the power of x. Check it. Cool. Perfect. Thank you very much. Okay, so now we're done with the part of just taking derivatives. And then let's talk something more interesting. So recall the formula of the price elasticity of demand at a certain point. We can think of it, well, you could probably see two definitions for the derivative. So first on an interval and the second at a point. So the interval one, we actually, well, we don't use it so often because we use it only when the percentage change for the price is more than 10%. And in the normal problems that we're dealing with, in realistic problems, we want to check for the smaller changes of price. So the formula for the price elasticity that we use is the price elasticity at a certain point of the graph, for example, of the demand graph, or at a certain point where we are in our company. So, well, in our market. The normal, most common definition, let's write it like elasticity of demand, and it is price, something like that. Maybe you've seen the other way around, here P and here D, but it really doesn't matter. I just want to make sure that we know that it's the demand elasticity and it is price elasticity, not, for example, income elasticity. Okay, cool. So we usually have a fraction of percentage change of Q. So this delta means the increment, right? The increase by how much quantity increased when price increased by how much. So usually the elasticity, the definition that we have is by how much is quantity increasing if we increase price by 1%. But then you can calculate with this general formula all the time. So what does it have to do with our derivatives and all that? Well, this can be rewritten as fraction. I'm going to explain minus in a second. So here Q over Q, and here the same with the price. So why am I taking out this minus? Because here I'm just taking absolute values of the increments. You know how you calculate percentage change? Second value minus first value over first value times 100. So that is the percentage change. If we expand here and here, we're gonna get, well, pretty much the second value minus first value, it's the increment, over the first value, and then the same for the price, times 100 for the numerator of this fraction and the denominator of this fraction. We can simplify. And then the minus is because of the nature of demand. We know all the time whatever happens, unless it's a given good, but no, we're not talking those. When the price increases, the quantity decreases, and the other way around. So that's why I prefer taking out this minus and here just taking absolute values of increments. So if I'm talking increase of price and then the quantity decreased, I'm just interested by how much, right? So the value, and then this minus is taking care of the negative relation between two. So, well, we can also again rewrite it as here we're gonna have we're gonna have delta Q over delta P times another fraction P over Q. So how did that happen? Well, we just know how to deal with fractions and divide one by another one. Yes, thank you. Perfect. So now what we're supposed to see is that this part is just the derivative of our demand, right? So this, well, with the minus. So this will be the derivative. Perfect then. We can again rewrite it. Let's do here and here. So this minus thing, sometimes we take it out, sometimes we don't. I like taking it out here in the fraction so I never forget it. But what you have to just know in the end is that price elasticity of demand is always negative. Well, I'm gonna write unless we have given goods, but we don't right now. Perfect. So this will be the derivative of Q with respect to P. So it is not the other way around. So it is a derivative of quantity with respect to price. So this derivative pretty much shows us by how much quantity is increasing if we decrease price by a unit times fraction P over Q. Okay, so this is the ultimate formula that I wanted to take out. And where did the minus go? The derivative is also taking care of the minus, because we'll see now the derivative is always will always be negative here. So okay, cool. Let's do the, wait a second, I wanna see it better. No, but I cannot see it better. But you see it anyways, it's somewhere on the bottom of your screen. For a given equation, the formula can be also, yes, but what does this dq over dp mean? It's just a different way to write the total derivative, right? So yeah, let's do it. Let's add this. I wanted to show you a little later, but that's cool because another way to write derivative is like this, and you probably have seen this, especially in some math courses. For some reason, professors like writing it like that, other than like that, which is faster, but it doesn't change the idea. Well, that changes an idea. Fraction of. This cannot happen on the whiteboard. I cannot just erase stuff by mistake. Here, multiplied by another fraction of p over q. And here, that will be exactly the same. And another way to write it, there is another way to write it. So instead of d here, we actually put delta. No, not this delta. Okay, the other thing. Then I'm not gonna do it. I don't know how to get it fast. You got it. If you saw it, then you got it. Is it? Well, it makes sense to listen to you. No. It's like this, but without the thingy. Doesn't matter. You'll see it in the presentation anyways today. Up, up. Partial derivative sign, exactly. And since we have here just one variable, p, well, partial and total are the same. Yeah, weird looking D. I think in LaTeX you put delta and it gets there. It's not like that delta. Well, anyways, let's go on with the examples. So the first one is the most standard linear demand function. And for the linear demand function, maybe some professors in undergrad made you memorize the special formula for oh, okay, partial, thank you. I'm not gonna write it later. Cool, so for the linear demand, we have always the same derivative. It is the coefficient of our p. So let's just write it here. There will be 19.a, right? So this thing equals the derivative. What is the derivative of this function with respect to p? Tell me. Minus 3, minus 3, minus 3. Yes, it is minus 3. Okay. So it's minus 3. Times. Oh, no, 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 no. Times a fraction. And a fraction of what? So I gave you the point, so p equals 3, just to get elasticity as a value, so as a number. So if p equals 3, then q equals what? Yes, 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 yes. So we do 150 minus 3 times 3. And that's what we're getting. And I'm not simplifying it. And it is negative, so we're all good. Every time you calculate elasticity, you should check, is it negative or no? And this one is. Cool. So now we can check example, next example. So that will be 3 over p. Okay, so here, what will be the derivative? The derivative will be, tell me. Yeah, tell me. Okay, everybody agrees? Do plus. Oh yes, if you agree, with minus 3 over p squared. Okay. Minus 3 times p to the power of minus 2. Yes, perfect. The same. Okay. Stop torturing you. It is like that. Let's write it in a fraction. Here we have 3, and then we're gonna have here p squared. Okay, so that will be times another fraction. We know that price equals 3. Oh, actually, yes, this I was supposed to change to 3. You already got the derivative, so I can just write the answer. And then the quantity, if price is equal to 3, not that difficult to guess. Okay, great. So here we see that we have a bunch to simplify, and I can actually do it. That we're gonna get minus what? Yes, minus 1. So this is not a coincidence. This form of demand function is called constant elasticity, constant price elasticity of demand. So the elasticity will always be equal to the power. We can see another example, like Q equals 1000 over P squared. So here you can calculate elasticity, you know how to do it. In whichever point it will always be the same, and we can just write that elasticity of the price elasticity of demand is equal to minus 2 in this case. So it is just the exponent. It is always the exponent of P. And I think many of you were already familiar with this thing, but just to refresh it. So no matter which coefficient we have, that's gonna be like that. Okay, now for number C. Okay, this is my favorite because I have to take a derivative. So let's first do the derivative, and you should tell me if I got it right, because you know. P squared plus 2 all that squared. Actually, is it even demand function? Well, let's see if this if this derivative is negative. So now I'm taking the derivative of the numerator, it's 2. Then the derivative of the denominator as it is, not the derivative, but just this thing. And then minus the derivative of the denominator, 2p, times 1 plus 2p. Now let's substitute p everywhere with 3, because that's our dot. That's our point. Oh, it's not 23. Yeah, it's a times 3. times, and here 3 squared. Okay, is it good? 3 squared, 2 times 3. Okay, seems like it is. Cool. Then, now I have to calculate it. That's even worse for me. Oh, type me the answer, please. Everybody giving a yay to minus 20 over 121? Cool. Oh, no, 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 not everything, no. Perfect, so minus 20 over 121. And it is a demand function. Our relation is negative. Actually, we could see that it is good because the major power of p is 2 and it's in the denominator. So for sure it will be like 1 over p looking function. Cool. So now for the elasticity. Well, easy, right? All we have to do, we already got the value. We have to just do fraction of 20 over 121 times, well, it may be 33 over 7, 3. No, not over 7. Why 7? We'll have 9 plus, oh, price. The way we write it is, wait, don't type anything yet. So we're supposed to type price over quantity. So price is 3. Then the quantity that we calculate here will be 7 over 11, right? Yes, perfect. So I want to get an answer here. Okay, so in here, for sure we're having 7 over 11. That's right. Okay, now we can see that this turns into, let's write it in one fraction. So we're gonna have 20 times 3 and times 11. Here we're gonna have 121 times 7. Right? Yes. And we actually do get minus 60 over 77. Okay, beautiful. Well, not so much. But at least we could simplify. Great, so that was C, and then the last one, finally the simplest question, without doing any calculation, but you could say that the elasticity of demand up is 0. Agree? Okay, perfect. Because it's a constant, and even without thinking of a demand, you just plot this as an economic function, as a mathematical function, and you're getting a horizontal line. We saw it yesterday. It doesn't change. Doesn't matter how much we change p. That exactly perfectly elastic. Well, it's not vertical. Well, it's vertical. Yeah, it's vertical when we type it. When we plotted in the economic scale, so PQ. Yes, perfect, great, thank you very much. In case we had here, let's say I want to give you an example of a function that looks like P equals 3. This is also a demand function. It means that whichever quantity you offer me, I'm gonna pay the price 3 and that's it. If you offer me 100, I don't know, cookies, I buy. If you offer me 3, well, I guess I buy 2, but well, my price is fixed. It's 3. And in here, tell me the price elasticity of this demand function. That will be infinity. Cool. So that just means that even if we don't increase price, we just really don't increase it by anything. It's always 3. But then the quantity can change as much. Perfect. Okay, great. So that was it. And then through the product rule, that was really not so necessary for our class, for our PSME first semester classes. Okay, great. So let's go on a break and